you. Many of the things that we know about the delivery of complex projects come out of a world that looks like this. 1950, Project Whirlwind, US radar defense. The 1950s US Polaris project pioneered techniques that are now standard in our industry. And yet, we've moved into a world that looks far more like this. Augmented reality, drones, reality capture, sensors, big data, building information modeling, are all becoming commonplace on our construction projects. We expect to be able to engage in a different way, much faster, monitoring and updating information in real time through more intuitive devices, through mobile and wearable devices. These technologies give us new capabilities in delivery. They're allowing us to re-engineer supply chains, to manufacture off-site, to alter design practice. They're also changing the deliverables of infrastructure projects. No longer are we an industry that delivers physical infrastructure. We are now an industry that delivers both physical infrastructure and digital asset information. This requires engineers with a different set of skills, the capability to work across disciplinary boundaries, to situate their deep knowledge and expertise in a broader context. It requires design, engineering, and construction organizations that can manage people, concrete, and IT, with all the complexity that brings, that can be home to digital natives and that can reimagine our physical realm. Infrastructure owners are beginning to use the digital data to manage infrastructure portfolios, to maintain interdependent infrastructure systems, and to make decisions about investment in new projects. The use of digital asset information is radically changing the nature and structure of our industry. I propose that we can think about built infrastructure, roads, railways, nuclear power stations, buildings, and the way in which they're delivered in terms of systems. A system is a set of components that work together. This might be a physical system, or it might be a set of principles and methods through which a process is organized. Systems integration is becoming more challenging as infrastructure becomes cyber-physical in nature. We don't always get this right. Take this already built but not operational airport. Maintenance is costing 16 million euros per month. It was originally planned to open in 2012. It's now planned to open in 2018 or 2019. The building inspector found 20,000 issues to be addressed before opening. This later rose to 150,000. A significant failure of systems integration in a European country. One of the many recent examples across the world. Over the next 30 to 40 minutes, I will examine the particular challenges of systems integration. I'll try to convince you of the value of starting with the end in mind. By looking at the ends and outcomes of complex projects, we might be able to better understand how we might set projects up, what issues emerge during project delivery, and the issues of the move from the project to gaining value in operations. I will draw on my research with major projects, Heathrow Terminal 5, London 2012 Olympics, Crossrail, and use examples to illustrate this transition. So the work we've done on handing data from projects to owners and operators, the work we've done on visualizing information to make good decisions, and the work we've done on connecting physical infrastructure and digital asset information. My vision is of a new generation of tools and methods for systems integration, bringing lessons from other industries, working with today's complex projects, Tideway, High Speed 2, Crossrail 2, and informing the changing supply chain, the digital engineering, design for manufacturers and assembly, the changing relationship with owners. And I'll round off the talk and conclude with a few words about the Centre for Systems Engineering and Innovation. Of course, many things in life are not a project. The organisational scholar Carl Weick reminds us that ends and beginnings are rare. Mainly we find ourselves in the middle of things, muddling through. But projects are future-oriented. To project is to throw forward. Thus, a project has an end, in that it was set up to deliver certain outputs, to achieve certain outcomes. A project's no longer a project when it's delivered. And I'm going to talk about complex projects. And we might think about the difference between a simple project and a complex project as the difference between going for a stroll in the park on a Sunday afternoon or climbing Mount Everest. The way in which we need to prepare may be fundamentally different. Most people take a year to prepare to climb Mount Everest. My thinking about complex projects comes out of some work around complex product systems, particularly around innovation in complex product systems like aircraft, experimental facilities, railways, and how that's different from innovation in mass production industries. Complex projects are high-tech, capital-intensive engineering projects of significant scale, relatively long duration. They require firms to work collaboratively across firm boundaries in project delivery. And this is work that I came across as part of David Gann's team at the University of Sussex, and then that we continue to work on here in Imperial. There's a set of thinking about systems integration in this literature. As projects are partitioned using breakdown structures, product breakdown structures, work breakdown structures, organization breakdown structures, we also have to think about how they're integrated. There's some tools and methods for this in the existing literature on complex product systems, on systems engineering, and in the engineering design sciences. I've been finding it useful to think about this with the kind of classic systems engineering V diagram. And so I'm going to use that as something to refer back to in the talk. How we get from the investment decision to operations and maintenance. We can lay out the different stages of the project. We can think about that as a process of partitioning and integration. As we move from the systems level to a subsystems level to a component level and put buildings and infrastructure together. And what's nice about the V diagram is that it makes us think about how we verify and validate the information at different stages. So how we think about the validity of information at a unit level, at a subsystem level, at a system level. The There's been a lot of thinking about project setup in the literature recently. The strategic governance of projects and how they're initiated. My proposal is that we need to look at the end of projects. This is where the value is realized by owners and operators. Take, for example, the BIM agenda. The value of digital data is not in its creation, but in its use through the life cycle. So I think there are some intrinsic issues that we need to address about handover, commissioning, operational readiness of projects. How can we, for example, use new tools to verify and validate the built infrastructure? I think there are some things that we can learn about how we do project setup better, with an understanding of the manufacture, assembly, operation and maintenance of infrastructure. And there are also some things we may learn about the emergent challenges of coordination on these large projects. As complex adaptive systems, new phenomena arise. I'm certainly not saying that we can prescribe everything at the start. Yeah? I'm saying that we need to understand how we put projects together better. In very early research, there was a study of the Tennessee Valley Authority, and Selznick argued that organizations are molded by forces tangential to their stated goals, which just shows how difficult it is to keep our focus on the ends in mind. So I led some research on how digital data was handed over to owners and operators, and we thought about this as a kind of process of passing the baton. This is the Olympics site in 2011 when we were conducting the research. This is it during games. And this is it in legacy. And we were thinking about the process by which data was integrated, brought together from the different construction projects. There's 70 projects, 14 venues and other buildings, 20 kilometres of roads, 26 bridges, hundreds of thousands of drawings and documents integrated out of the supply chain. And the challenge there is about getting high quality information from the supply chain at the end of construction, when they're at peak construction on site and yet people are asking them also for the digital data. And they put in place a T- process, a process of trying to keep up the momentum around getting digital data out of the supply chain and crucially not missing that window of opportunity to get the data, because it's difficult to check once the teams have disbanded. We looked then at how that was handed on to games and legacy users and the kind of strategy challenge of engaging with organizations that will use the data after handover. One of the people we talked to in doing this research said, you have to get quick off the blocks doing the Olympics, and if there's one lesson learned, you need to get a plan off the shelf as to how you want the data structured. You need to know what you want at the end of the project so that you can stipulate it at the start of the project. One of the interesting things about this study produced practical outcomes with the Learning Legacy report, but it also provides a contribution to the research literature, because much of the work on coordination is about different disciplines of engineers working together over long periods of time. There's actually very little work on this kind of handover, this sort of organizational handover, where some teams are handing over and then disbanding and leaving other teams to pick up the infrastructure and to do work. And most of the work that has been done in that area has been on things like the emergency room, where someone is running in with the patient and handing them on to another medic. A situation in which the same professionals are working together over time. This is quite a different kind of situation. So hundreds of engineers handing over to a completely different organisation to take forward the facilities in legacy. A second area that I would like to talk about then is work that we've done on visualising information to make good decisions as part of this process. I worked on this during my PhD in the late 1990s in Loughborough, developing applications of virtual reality, working with housing developers, and thinking about how a model of the project might be shared by different disciplines. I've also done work looking at how people use representations in design practice and looking to understand how they make decisions from representations. And building on this work on visual practice, we brought engineers, designers, the owners and operators that were their clients into the immersive virtual reality facility at the University of Reading to look at their designs. So we had research projects on design for safety, looking at lessons learned from projects, looking at the issues of design into construction, and we had many construction underground projects come and visit us at Reading. So King's Cross came, and they brought a couple of their friends. They brought Victoria Station and Tottenham Court Road. Bond Street also came in, and they really appreciated this ability to get different parties into the model, to be able to see it from the inside and to walk through it together and to make decisions based on that. And we wanted to take that capability out of the university to our industry partners. And so we built a 3D mobile visualization environment. And this is the first time it was ever put up, and I can see Max, who's the research fellow, in the audience. And the really key thing about this is that what's unique about this is how fast you can get the facility up, how portable it is, and how quickly you're into viewing the model, into the work of the engineering, the thinking about how we do infrastructure better. We tend to say that you can put this up in less than an hour. Actually, as you'll see on the slide, they're into the model in just over 30 minutes. There's been a lot of discussion about head-mounted displays, Oculus Rift, HTC Vive. My view is that for the kinds of conversations we want to foster in construction, this kind of technology has real value because it gets engineers to navigate the digital model together. So we took it out to Crossrail's Young Professionals Conference. We've taken it out to the Bentley Technology Day. We've used it in the university. And it's now in Crossrail's system-wide offices, being used by engineers who can bring their own models into the facility and can work together with them. And the research has moved on to look at the interdisciplinary design reviews that are taking place in this space. And so the third thing that I would like to talk about is that relationship between the, I should say physical infrastructure, the physical infrastructure and the digital asset information. And I first started to think about this when I did work at Heathrow Terminal 5. And there I was looking at the single model environment. And the place where I was told to look was the roof sub-project. The roof sub-project is an example of a highly effective sub-project within the project. And there they were playing with a range of different technologies to explain the construction process. And I really understood how this is not an industry like software. We don't just build digital things. We also then have to take those digital things out of the computer and build them at scale in the real world. And the roof at T5 is the size of 8 football pitches. And so it's a big structure. And moving from the digital model to that big structure, there's a kind of process of doing that move. And working with colleagues in Crossrail, we've been thinking about how you keep the requirements, the digital asset information, and the physical assets connected. We did some work bringing Airbus and CERN together with Crossrail to explore this issue. All 3 of those organizations manage large digital data sets. They're all involved in complex engineering problems. And we were thinking about how you manage those large digital data sets as you move from information that's used for decision-making and delivery to asset information as a deliverable. This is the Department of Defense guidance on how to do that, and it was brought out in 2013. And I think it shows you how the heritage of some of our ideas come out of this paper-based era. And one of the challenges is implementing these sorts of processes in a digital world where there's so much more data, where people are used to being able to interact in real time, and how do we have good processes to ensure that the engineering is robust in this sort of environment? One of my students, Guoyang Guo, has done some work looking at the interactions that go on in digital systems in the delivery of projects. What's novel about her work is that we're taking data directly from the digital system, and it's helping us to start to understand the pattern of interaction in delivering complex projects. But again, this is a world that's transforming. There's a lot of information on this slide. What I really want to use it to show is the difference between the timescales for physical infrastructure and the timescales for digital technology. And so the 3 projects that we studied in this study start in an era in which some of us were using the BBC to do some of our early computing at home. They moved through the era at which the internet was made public, and through an era in which the iPhone came out. And I was surprised to find that the iPhone only came out in 2007, because it already feels quite a long time ago. And so even in the delivery of these projects, there's generations of digital technologies that the project has to deal with. And yet, if you look at a railway, then a railway is designed to last for 100 years. And so there's even more change in the operation phase. And so I want to highlight the difference in technology life cycles between built infrastructure and digital technologies. As we move into a data-rich world, then we face new challenges: cybersecurity, information overload, coordination, and we have to deal with those on our projects. In fact, the railway project on this slide, it took a decision not to upgrade technology. It held technology stable through the life of the project. The engineers at the end of the project had a bit of a culture shock going back to their organisations, which had moved on. And I think it's interesting to see how the current generation of projects has started to implement an innovation programme within the project to allow for adaptation and change around technology. Because we live in this world where technology is moving forward more rapidly than the underlying infrastructure, the significant infrastructure. And thinking about that in terms of the V diagram, there's been work on how easy it is to do kind of modular innovation in an industry like construction, because organisations own the bottom of this V. They own the components, and so they can innovate on those. The challenge, of course, is the systemic innovation. I think the innovation programs in the major projects provide a vehicle for that kind of more systemic innovation. So bringing systems engineering and innovation to built infrastructure. I'm delighted to be rejoining Imperial, working with colleagues in leading a research centre that's bringing systems engineering and innovation to civil infrastructure. Imperial is a great place to be doing this work, as it has deep knowledge in the engineering and computer sciences and a focus on educating the next generation of engineers. A vibrant research community, and I'm delighted to have colleagues who are interested to work around these topics. And the research benefits from centres and labs across the Faculty of Engineering, the Dyson School of Design Engineering, the Energy Futures Lab, Data Science Institute. So our approach is interdisciplinary, cross-sectoral, international. We're collectively seeking to bring systems engineering and innovation to this industry. My colleagues and I are working in areas around systems design and optimization for design for manufacture and assembly, around visualizing interdependencies within and across infrastructure, around the verification, validation, and handover of information for through-life value. My personal vision is to develop next-generation tools and approaches for systems integration. There's substantial data sets at the heart of infrastructure projects, and we have to use them more intelligently to develop new ways to visualize interdependencies, interrelationships, interactions, to help engineers with the integration challenges that they face in achieving successful project delivery. Research is never an individual accomplishment, and I'd like to thank funders without whom this research would not be possible. I'd like to thank colleagues. I would like to thank people who've worked with me on research projects, and I'd like to thank the institutions through which I've studied and learned. I've had the real privilege of working with many people who are missing from this slide as well. In an inaugural like this, it's not possible to cover the breadth and depth of research that we've been engaged in over the last decade. And so I would just like to point to other adventures, and I would like to extend an invitation to you to join us as we take this agenda forward. So as we come to a close, I would like to argue that this is not an ending so much as a moment of transition, and to invite you to join us on the journey, working with and informing the next generation of complex projects, digital engineering and design. Yeah, I'm looking for industry partners to work with us, looking for researchers, I'm looking for doctoral students to come and join and take this agenda forward. In a data-rich era, I can see us developing new ways to bring people together. My ambition is to develop a new generation of tools and methods for systems integration.